All right, we'll go ahead and get started. My name is Matt Delacluse. I'm General Manager of RAECO Rents. I'd like to thank all of you for taking the time out of your busy schedules to join us for our webinar, Assessing Unknown Odors and Chemicals. Our presenter today is Jim Cornish. In this 45-minute webinar, he will cover the following: intermittent odor and chemical exposures, how to assess chemical toxins in confined spaces, measuring multiple gases simultaneously, using NIST EPA reference library of over 5,000 gases to identify unknowns, and ask the expert. Your questions will be answered. Jim Cornish has been working in the field of environmental instrumentation for more than 20 years. He joined Gasmet Technologies, Inc. in 2008 to provide application, instrumentation, and technical support. He has extensive hands-on experience with many field analytical measurement technologies, including gas chromatography and optical measurement. Jim is actively involved in AIHC real-time detection chemical detection systems PDC. Jim received a Bachelor of Science in Applied Chemistry from Deakin University, Victoria, Australia. Now I'd like to turn the microphone over to Jim. Welcome.
Thank you, Matt. Thank you, and good afternoon to all the attendees. Thank you for your time. The presumption is you can see my screen now. So what we'll be doing here is presenting really the assessment of unknown odors and chemicals and how that's applied in the FTIR multi-gas measurement technology. We'll work through a way of what it can do, how it can do it, and then tie it together of how it can really be used as a powerful tool to solve air quality issues with mystery odors and chemicals, etc. So starting at the start here, the two in FTIR technology, there's really two functionalities, dual functionality as we call it. It's the ability in the first instance to protect employees by assessing their exposure, and we really classify this under the quantify the known title. And what that is that you can have a list or an application on the left-hand side of the screen. We're talking about an application library that can be up to 25 gases in one application library. And then on the right-hand side, we'll talk about the spectra and how that's determined. But you can go out into the workplace and actively assess the exposure of employees to particular toxic chemicals, and that is that you really know what you're looking for. You're just trying to quantify, look at whether you need to put any extra controls in place or whether the appropriate protection is in place for the employees. So that in itself offers a certain level of analytical power. 25 gases can be measured simultaneously. So of course that in other instances, maybe having to take out multiple instruments to achieve the same level of testing. The second area, and that's truly its strength of the FTIR, its real power, is this next one, is being able to solve air quality problems by identifying the unknown. So when you're called out from a worker has a particular smell, odors that are coming into the workplace that they're not comfortable with, that you're being called out to solve these problems, then this is where the technology can really shine because of its analytical power, and hence we're assessing the unknown odors and chemicals. So that's the two things we'll talk about as we go through. But as A is, if you know what is in the air, you can quantify it. B, if you don't know what's in the air, then this technology can be used to help you identify the unknown. So in a the big picture situation here, this slide, what we're just trying to do is pull together in a big picture scenario of understanding the FTIR. So acronym number one, FTIR, Fourier transform infrared. Also just can be really thought of as multi-component gas analysis. That's what it's really offering for FTIR. And what we see is the gentleman here with the analyzer on his back. He is sampling a cloud, a contaminated cloud. All we're trying to illustrate there is inorganic and organic gases. A mixture is being drawn into the analyzers, as shown on residing on his back, and the gas is being analyzed. And then in 60 seconds or less, and we'll talk about that momentarily, in the palm of his hand, he can have the readout for those 25 gases. So it's being sent by Bluetooth to the palm of his hand, and then he can have a spreadsheet of gases, or he can see a specific gas. And those 25 gases can be taken from a library or drawn from a library, a master library of 335 gases, so they can be changed as the application seeks that to demand different gases for different applications. If we try to put in one sentence, essentially what FTIR is, it really is a combination of optical light and mathematics. So those are the two that come together. And the other sweet caveat of the technology, as shown in the bottom right there, is it never needs recalibration. And so we'll momentarily show you how we get away with a big statement like that. So here we're showing the real, just one technology slide on the spectroscopy. So on the left-hand side, what is the basis of the theory is basically infrared spectroscopy, been around since the 1800s. The two gentlemen, Beer and Beard-Lambert, were the real two pioneers. And they discovered that all asymmetric molecules, so what's an asymmetric molecule? Just has two different atoms. So here we're illustrating the water molecule, hydrogen and oxygen. Then they all absorb light in the mid-infrared. That's a region of light, specifically around the 4200 to 800 wave number, 2.5 to about 12 micron, thinking that. They all absorb light, and the other beautiful thing is that they all do it with a very unique fingerprint. Excuse me, just like you and I, we all have unique fingerprints, and so do the molecules. So the gentleman Beer and Beard-Lambert came up with the relationship that the y-axis, the absorption of a gas molecule, is equal to an absorptivity times the path length times the gas concentration. Hence, if the epsilon and b is being constants, then if you measure the absorption, you can get the direct concentration derived of the gas molecule. In the technology, it's easier for us actually to say what cannot be measured than what can. So the cannots are quite simple. They're diatomic homonuclear molecules, that, as illustrated there, oxygen, hydrogen, nitrogen, chlorine, fluorine, etc. The permanent noble gases, neon, argon, krypton, etc., they cannot be measured. And there's really just one outlier, and that is the hydrogen sulfide molecule. It's an extremely weak infrared absorber, and so it's essentially not possible to measure it with this technology. So that then means that everything else is essentially on the table that can be measured with the technology. So all the organics and all the inorganic gases, with the exception of the H2S. The FTIR is just explained briefly on the right-hand side. The pioneer there is Dr. Albert Michelson, a US physicist back in the 1890s. He was essentially trying to find a technique to calibrate the speed of light. And this is his interferometer, as it's called, as a diagram. And basically what happens is light is basically sent through a beam splitter where two mirrors exist. And it's sent through different phases of construction and deconstructive phases to produce, at a rate of about 10 times a second, an interferogram, which is essentially an interference pattern. That interferogram has basically light frequency versus it's on a time domain of where this mirror is. And so what the next step after the physical collection of that, then the gentleman whose name was associated at the front end, the FT, is in fact Fourier. Jean Fourier, the French mathematician. He has a transformation that can transform the frequency, which then becomes the x-axis, to intensity, the y-axis. So it gets transformed. So you've got frequency versus time to frequency versus intensity. And from that, we derive the full infrared spectrum across the region. Now, why we say there is no calibration required is that with every FTIR, you need this internal neon helium laser to very, very accurately and precisely map the movement of the mirror, this one mirror that moves. And that basically internally calibrates the x-axis so there can be no drift. And on first principles, the molecules, just like you and I, and our fingerprints can't be changed, either can the molecule's signature. So that means the only axis that does change is the y-axis here. And how we overcome that is with a daily zero calibration of the instrument, taking a gas, typically the nitrogen gas, to zero the instrument. So that's kind of the foundation of which FTIR is built on. So what you're getting out of this is a very fast and extremely accurate analytical technique for measuring many different gases. So just to put the hardware into perspective, it's a little bit sensitive here. If we're looking at an FTIR, were to take the top off, you would see your normal electronic boards, circuit boards, etc., as illustrated up there. The two key components of an interferometer or of the FTIR are to the left-hand side, the interferometer. It's seeing there just the movement of the mirror. It's used by a voice coil. It's a very small, that's exaggerated. The actual movement's only about 0.14 millimeters, but making that compact and rugged, vibration insensitive is a key component to that. And now in the second side, on the right side, the gas cell. So there are no sensors. The gas never touches a sensor. All that's happening is the gas is coming through a gas cell. That gas cell, if we go back to the Beer's law, is the B. We need path length if we need to get sensitivity. So we take a cell that's approximately 3 to 4 inches long, and then using gold mirrors, we can get multiple passes or reflections. And so one cell 4 or 5 inches long can have an effective path up to 30, 33 feet long, 10 meters long, which then means that you can be measuring gases down in the sub parts per million. Gold is very good with transmissivity. It's also great for jewelry. However, it is not necessarily corrosion resistant against some aggressive chemicals. So it's important to coat that, which is coated with a nickel rhodium coating for the cell and the mirrors, so that any toxic corrosive gas, your ammonias, your acid gases, etc., will not have any negative impacts on that. So the light is coming in from the left-hand side of the cell from the interferometer. Gas is going in immediately, and then on the other side of the gas cell is the detector. So as once again, there is no sensors involved. There is no ability to poison or kill a sensor, etc., in this type of technology. So now let's talk specifically, get into the nitty gritty. What's it going to do for me? Here's an application in the semiconductor world, for example, where you can have this list of gases. So here we have 25 gases, essentially, components. So you've got your arsine, phosphine, many different other acid gases and silanes, etc., that can be all measured simultaneously. You're getting a direct readout here in gas concentration, your units, typically parts per million volume, your calibration or measurement range, meaning you've got calibration points over a given range. And then the one very critical or very important component of an FTIR is this last column, referred to as a residual column, where you're making a statement, a quality, a QA/QC statement to ensure you've got successive analysis. And I'm going to draw that into the discussion here momentarily. So also, of course, alarms and visual and audio alarms can be set in, but that is essentially the deliverable. When you're looking for known components, you're drawing up this application library of your 25 gases on that. All right, this is just showing the library of over the 300 various gases, 350 various gases that are available for integrating into an application library. The other side is just to also highlight the sensitivity we talk about, again, going back to the principles of the absorptivity constant that's in Beer's law, then that dictates the sensitivity of the technology. So here's the sensitivity in brackets. When measuring 60-second measurements, then acrolein will have a sensitivity of about 0.13. You can see some molecules are more sensitive than others. Your, methane down to 0.03, your dichloro, methane, all those. But typically that's why we call it sub-ppm. Some molecules, there's a few that actually get down into the very close into the parts per billion. Nickel carbonyl is one of those. Sulfur hexafluoride, etc., are very strong infrared absorbers and can be measured down at low, very low parts per billion levels. Again, typically we're talking in the sub-ppm 0.1, 0.2 detection limits with the technology. And remember, if we wrote number 26 on the screen and put hydrogen sulfide, you would see a number that's greater than 100 ppm. So you can see how much of an outlier it tends to be. it's a bit of a time lag, unfortunately. I apologize. Let me go back. All right. So now let's turn our attention to this whole question of the solving these air quality issues. So up until now, we've really, as I say, we've dealt with the situation where we've got our application library. We kind of know what gases we want to test for. But what about the situation of incident response, where you've been pulled into a situation where you don't know, you've got some perhaps ideas that where the odors could be coming from, etc., but you really don't know what you're dealing with. The hazmat community, of course, is dealing with the 911 call comes in on a daily basis. This is what they're responding to, is the unknown. And so the technique here is certainly very well received in that community, because you've got a tool that can tell you in a timely fashion what is in the air. Matt, is it possible, Matt, just to get control, because I'd now like to show how that all works in the software side of things.
Sure, let me change. All right. All right, you are now the presenter.
Okay, all right. So now I'm throwing over to the software, the CalcMint software, and we'll sort of just explain how that's happening. So what I'm showing here is a spectrum. We kind of derived how that all works and how that's all coming together. On first principles, if there's nothing in the air, there's no absorption. So I'm presuming you can see my mouse. These areas, there's no absorption here and here. But lo and behold, there's quite a strong absorption bands here and here. So there is definitely something in this sample, something in the air that's been measured. Now, if you had perhaps a PID or even an FID, but a PID, then you could come up with a number. So you have a total number here that's illustrated as a TVOC, 218 ppm, and that's all you would know. And I'm sure the next question, well, what is it? What's in this sample? Is it one gas or is it multiple, etc.? So this is the difference of the power of FTIR. So we'll take it from just one answer. So now we won't change the sample, but now we'll go to a different application library. Okay, so again, I'm just drawing it. That was the same sample we're dealing with. We haven't changed the sample, but now we've put a list together of 25 gases. And it's saying from this application, from this sample of the three solvents, in fact, what you have there is you have acetone with 144 ppm. You have ethanol with 42 ppm, isopropyl alcohol with 28 ppm. You have a bar graph just representing across the range. You could put an alarm for concentration alarms, etc., etc. And you have this residual value that's telling you that you have a successful analysis. Okay, so what is meant by that? Well, what if you didn't have one of those components in the application library? Would you have missed it? What would happen? So here's the signal of an unknown. So what I'm about to do is take one of these gases out, and it doesn't matter which one it is, but let me say that I'm going to take the ethanol out. Then what has happened is been a reanalysis. Same sample, of course, we have still got the complete sample, but now the application library is devoid of one of the main components, which is the ethanol. And so it is told the user through this residual column that you have an unsuccessful analysis, which is the trigger to say you have an unknown. There is something in the sample that is not in your application. So this is where the strength of the technology can be put into place to solve the air quality, assessing what unknowns and the chemicals that you're dealing with. So the next step for the user is simply to change to a library search function. So what we've done here, we're still dealing with the exact same sample. We've basically taken the water and the CO2 out of that. We have loaded the NIST EPA library. So that contains 5,224 currently. Normally you don't need to do this, but just to kind of illustrate what's going to happen is it's going to go through all these spectra to look for a match. So because again, first principles, they all have a unique fingerprint, unique signature. So with that in place, the user is simply going to ask for the software to scan through the reference database and do a statistical match on what it sees here. 12, 15 seconds or so, depending on the computer. Then what it's showing the end user is that here in this sample, it believes statistically there is acetone with a very strong 98% fit, this concentration, the ethanol, again, 96, 97% fit concentration, and the isopropyl alcohol, this particular fit and concentration. So with that information, the user can go back to their original application library. Again, we're not changing the sample's staying constant, and can look their way through and say, there's our acetone. Yes, we had the acetone, isopropyl alcohol. There's methanol, but it had, the third gas it pointed us to was the ethanol. So let's add ethanol to our application library. All right, and so we'll reanalyze, and now it's come up with a successful fit. The residual value is all green. Green is a successful analysis, so it's the three major components in this sample have been identified and quantified. So now the user can put the controls in place. So essentially that is part of the power of being able to quickly assess, go in, assess, make the measurement of the sample. Even if it's a 60-second, it'll give a great indication if there's anything in the room as to any of the absorbing IR gases. It will be measuring those, and then the user can put that that sample, can compare it against the reference library and let them help them identify what the unknown odor or chemical is that they're dealing with, and hence then look to likely sources and put the controls in that are necessary to affect a timely response. Now if I go back. So what's happened here is essentially we just illustrated here how we've seen the yellow and the red through the residual, gone through the performing of the next step required. And so what you saw was essentially the spectra put through, and there's two references libraries that do come into effect here. There's a Gasmet reference library where we can quantify and identify, and then there's the NIST EPA library as well, where we can do the identification of the unknown gases. So it's quickly, once the spectrum has been measured, can be quickly put through the software, the advanced CalcMet software, to allow the identification and the quantification of these gases or unknown gases in the workplace. Here's just a couple of case studies. One little story, just how simple things can be, is that in one of the Texas universities, I'll leave them nameless at this stage, but essentially it was doing a startup, a training. We were getting the people familiar with the zero process, and we'll show that momentarily. So zeroing the instrument, etc. Training starts in the morning, going through things, break for lunch, come back from after lunch, and we more hands-on, getting people to get familiar, do those nice zero, and then we start to make some measurements in the room, and lo and behold, up come some unknowns in the spectra, and we then put it through the next step. We sort of shake our head and say, what's going on? And then it finds Freon 134A, and in fact, right on top of the EH&S department there, that had a leaking air conditioning system that had been coming down, and had not known about it, essentially because you were, again, it's an odorless gas, but there it was showing up in the infrared spectrum once we had done the zeroing process as an unknown, and we were able to detect it through the use of the advanced library search. In this next application, here's a case study where on the right-hand side, the response team was called in to St. Joseph's Hospital in Michigan, Ann Arbor region, and so they were called in because of this mystery odor that was happening, and so they the team brought in their Gasmet analyzer and asked to check in various components, areas of the hospital, because there was a huge concern that they were dealing with formaldehyde. There was formaldehyde, and so the employees were very uncomfortable, very sensitive to that. And so they ran the testing and were able to determine that it was not formaldehyde. In fact, it was a toluene leak that was coming from a floor above, where they were dealing with formaldehyde through the formalin solution, etc. But they were able to determine no, that was not the source of the odor or the problem. It was from a source upstairs, where they were able to both identify and then take the necessary remediation steps to solve that, to stop toluene getting into the system. So again, it was just the beautiful thing. The user there, Bob Lovelace, he was very pleased with the performance of the instrument. Wrote up a little report and included those kind words on the performance of the FTIR to solve that air quality issue where people are evacuated, and they needed the tools to come in to solve in a timely fashion what they were dealing with there. So operation, what is it? It's one of the optical measurements. Generally an easy way to operate. So we'll quickly a simple technique to use. Here we're showing that it can be run certainly AC power or battery power. Your two options: battery giving you the autonomy to walk around, make easy measurements in various rooms very quickly. Warm-up time is quite short. It's really related just to the time that's from where it's been stored and the temperature to getting it ready. So typically 5 minutes or less, you'll be ready to make your measurements. As we'd mentioned before, really the most critical thing that you're doing with the FTIR, because of the internal calibrations taken care of for you, you're doing a zero or a background, the same words are used, but a zero calibration where you're taking a inert gas, typically nitrogen, a little cylinder of nitrogen's used, and putting that through. Nitrogen, of course, has no absorption, so it's 100% transmission. So that's setting that 0 point. So once that's done, it takes approximately 3-4 minutes or so. Push a button here, run it through. Then you're ready to operate the FTIR for the day. No spans or any other gases or consumables are required. So then the instrument's ready to go out into the field, into the plant, into your rooms, into your testing, into your laboratories, etc., to perform the testing. The readings can be updated quicker than the 60 seconds. 60 seconds, as we've dealt with before, gives us the optimum amount of sensitivity on that. But often 60 seconds can be quite a while if you're looking for leaks. You're doing survey work, so you can go as quickly as every 5 seconds or 20 or the 60. It's just a trade-off in sensitivity. You're going to lose 5 seconds. It's great for leak detection. You can walk around and be very sensing or testing valves, whether you're in an operating room around biomedical equipment or medical lines, around bottles, then you can very quickly assess leaks. It tends to be less sensitive by about a factor of 3.5. And if it's 20 seconds, again, it's a compromise between a survey and about 1.4 times less sensitive, but you're getting quicker information coming back at you. Data then can be, of course, we mentioned you're going to get your every 5, 20 or 60 seconds updated readings. You can have alarms set with those visual audio alarms, and then it can be saved, the spectra saved, and also savable as a text file. So then you can actually open everything up in Excel, have date and time. There's a GPS with the PDA that comes with it, so you'll have spatial information as well, all collected together, video and camera on the PDA. So it allows you to kind of take whole care of the incident in that and have the documentation to assist you in writing up a report at the end of that time. Instrument maintenance, again, the nice thing about an optical instrument such as the FTIR, it has a relatively low cost of ownership, no sensors, etc. to replace. So all you're dealing with is your zero gas, the nitrogen. You usually want quite a good purity. If you're trying to get to low concentrations accurately, we're calling a 5.0 or a 99.99% purity. A low consumption, you're only consuming about 10 liters per zero of that. So and can be sourced locally. There's nothing proprietary about the zero gases of it. And the second component is a particulate filter. Yes, we are screening out. The only conditioning that's happening is to pull out dust levels of 2.5 micron or higher from sitting on the mirrors, so on call, causing no maintenance. So they should be periodically changed, perhaps every 3 months. It really depends on the application, but there's no a very low cost of ownership there just to replace the filters. And the other big statement down the bottom is that people are so used to sending instruments back once a year, but there really is no requirement to send it back because of the internal calibration done by the laser. You also see every time you do a zero, you have an optical health, you have a statement of the quality of the instrument. So that can be documented as well for the ongoing maintenance, etc., of the instrument. Validation, FTIR, it is received by NIOSH as method 3800. So it's a valid analytical technique. The US EPA and ASTM are standard methods as well, so that you follow method 3800, then you can be in compliance for testing of various gases, etc., that can be measured by the FTIR. You've got other third-party documentation, etc., but it all ties into the very strong analytical specifications of plus or minus 2%, essentially linearity or accuracy when measuring the gases. So pulling together sort of the benefits of having a technique like this, like FTIR, is you've got a way of certainly measuring very productively 25 gases simultaneously drawn from this master library, so adaptable to many different applications. Again, where you are really quantifying the known, where you're going in knowing potentially what you're dealing with, then you've got a tool that can very quickly you walk in and be measuring these up to 25 gases simultaneously. And then that next level of power of when you don't know what you're dealing with, when you're being called in for the mystery odors, the smells, where there's a sensitivity in the air from the employees about the air quality, and they're smelling headaches, etc., dizziness, then you're able to go in with a tool and be able to identify what's in the air. And just as powerfully as we get comments back, certainly in the hazmat world, where they get called into schools commonly and they can do a sweep, and with a lesser power equipment, with their their PID and gas detector, they can rule some things out. But a technology like this, they can leave knowing, they can give the indication that there's all clear, there is nothing in the air, because it's powerful enough, remembering of just the gases that cannot be measured, and they can really very confidently say, no, it's all clear. You can send the students, you can send the people back into the workplace, and there's no apprehension of that at all, because the spectrum is telling them exactly what is or isn't in the air. Ease of use is certainly, again, as opposed to perhaps a gas chromatography system where it needs more intense training, etc. You have a tool that can be, with usually a day's training, can be very effective, can be used by multiple people in a safety department, etc. Usually have a couple of key users, but then people can use it across, be passed to the instrument to go out and be effective with its measurements. The validation results, this is a key thing, I think, is that you've got that spectrum. It's actually tamper-proof. Once it's been measured, it cannot be changed, date, time, it's all meta-tagged, spatial information if it's there. And so whether you want to have a second party look at it, your colleague, you can actually use overlay spectra. So it tells you the truth. There is no way around it. It's basically to lie to you. If the chemicals are there, they will be there in first principle basis. So it's a very strong way of going back and double checking and or validation thereafter on that. So low cost of ownership. We've talked about here with no sensors to replace, carrier gases, calibration gases, etc., etc. They're all basically being able to be removed from the cost of ownership, and so you're really just talking a zero gas and the particulate filters. And the nice thing is the sidestepping redundancy, that the list of gases continues to grow. Originally, when this started back in about 2008, you were talking about 170. Now we're in excess of 300 and climbing. So as new gases, new freons, new mankind's bringing out to the market, they can be added to the measurement library. So you're sidestepping redundancy to the future of the instrument as your applications expand and are required. So with that, I'm more than happy to take some questions and any further discussion. But thank you for your time this afternoon.
All right, Jim, I got a couple questions that have come up. One is the question on the accuracy of the unit. What does the calibration gas need to be certified to? You said 99.99%?
5 R's, yeah. So 99.999 is the recommended. That's also referred to as UHP, ultra high purity nitrogen. Now, that's if you go less, of course, it just allows the bottle supplier to add more contaminants. So if your objective is trying to use the technology to be measuring sub ppm levels of contaminants, then you want, of course, your zero bottle not to contain those contaminants in the first place. Otherwise, they will be zeroed out. Hence the reason, the recommendation of the UHP. Without sort of going too far in that discussion, you can do a zero off ambient air. It's, there are many good reasons to use the zero approach using a nitrogen bottle, but in a pinch, should you wish to, you can zero on ambient air. The big proviso is, or of course the most important thing is, that you are not in an area where the contaminant could potentially be. Same reason you would be zeroing it out. So you need to be back in what you would then call a deemed location for that zero. In terms of accuracy, there's two statements that come together. I mentioned one of them is the plus or minus 2%. So that's deemed to be the linearity of all the gas standards or calibrations done with the instrument. The second is application orientated, which is basically it's less than plus or minus less than 4% of all the cross interferences possible from any other gases. So that's application derived, because every time we make a statement of accuracy, we need to know, is this just the component in ambient air, or is there in fact a mix of contaminants or components, etc.? So one needs to understand the application fully before a true accuracy statement can be measured or can be provided.
Okay, the next question, have you done any testing with the Gasmet for post-fire monitoring, or are there too many byproducts of combustion to get a successful scan?
The origins of it's a very good question. The origins of Gasmet, actually, which started in the mid-90s, has been combustion. FTIR is an excellent technique. It's actually a marriage made in heaven for combustion. CO2 and water vapor, of course, if life was perfect in combustion, would be all you have. But then you have your inorganics, you have your acid gases, and you have your VOCs. So all measurable with FTIR. So moving along then in fire testing, there's been quite a bit of interest because of the, I guess, the occurrence or the high occurrence of cancer deaths related to firemen and investigators, etc. So been involved in studies where you're doing, yes, VOCs, we're doing other aldehydes and aromatics. At one point in time, of course, people just used CO as an indicator, then they stepped over to HCN, and then they still realized, the researchers realized that no, there's many more things, particularly with your couches and everything, all the plastics and all things like that combusting. There's a lot of acid gases floating around. There's a lot of other aromatic and VOCs. And so, yes, there's been one application library that we've tailored to fire testing for assisting them make sure they protect their breathing zones, etc., when they're going in, when to take off their masks, their breathing apparatus, etc.
Okay, next one, is there a real-time display of the results on the device?
So the operation of the DX40 has two modes of operation. One mode is the usage of the PDA, and that's really what we mostly highlighted there in the presentation. And so with the PDA and the Bluetooth sending the information, whether your measurement is every 20 seconds, say, for instance, as an example. So every 20 seconds, the user will see updated readings for up to 25 gases on the PDA. The PDA would be then saving that information to a storage card. It's a RAM card that's non-volatile, so they won't lose it. So they will have that. So the second option is to actually operate the 4040 from a laptop or a tablet. Now you're dealing with a bigger screen, so you not only can you see the gases updated every 20 seconds, you could see a spectrum if you wish to, but you can also start to see trending. The disadvantage of the PDA, it's a smaller screen. It's all meant to be autonomous, that you can have this in the palm of your hand, but you don't necessarily get any history with it. So if you're longer term, if you're wanting to set it up for longer term monitoring, people will use the PDA or a tablet, and then they can quickly assess, okay, now it's on the way down, things are looking good, we're cleaning up nicely, or what the situation may be in effect. So yes, it is seen.
Okay, next one. I get some calls for mystery odors in commercial buildings, but more often I have homeowners calling because they have an unknown smell. Would this be a good tool in that situation?
As an investigative tool, absolutely. The spectrum, as mentioned, is always produced, and you can very quickly assess from that spectrum what you're dealing with. Is anything out of the ordinary. It's also a bit of a pacifier. You can show, you've got a technique where you can show there's nothing there as well. I mean, there's sometimes people just want to go early on a Friday and they can imagine something in the air, or you can, if there's a true smell, an odor, you can go in and you can show people what they're dealing with. Of course, you're going to see your CO2. I mean, from indoor air quality, your surrogates, your CO2 is obviously a go-to to figure out what sort of ventilation is happening. Yes, it's an expensive CO2 analyzer, so you're not going to buy it for that. But to the next level, you can get down into the very low levels of the formaldehydes, of the other VOCs, etc. So it's a tool that can be used to assess the quality of the air on that. So yes, then there would be no problem there. Commercially, it's obviously when people are being disrupted, production's costing money, people being out of buildings, not being productive. That's generally where the cost effectiveness of the technology is associated more to the work environment. The homeowner environment is applicable for sure.
Next one is, what is better, a PID or the FTIR?
Well, they're different tools, that's for sure. The Mustang or the Rolls or whichever. And yeah, as we illustrated there, certainly PIDs have a very important role. They can very quickly assess a hot spot. Now, of course, that they have limitations of what gases as well, but they assess a hot spot. If it's a one chemical hotspot, then you've assessed the problem right there and then. But if it's a unknown chemical or a sample, then all you know is you have a total VOC of some proportion, not knowing what it's fractionated down to, hence the analytical. So it's a higher analytical power tool, but it's really after the PID has only given you limited information and you need to know the rest of the equation, the rest of the answer.
All right, and the last one I have right now is, what are the operational costs, i.e. send back for service or purchase of consumables for this unit? Basically anything that cannot be performed or replaced by our in-house service technicians.
Yeah, so as mentioned, it's a very low cost of ownership. We're really on an ongoing basis dealing with really the two components. You'll need a zero gas. We're picking on the nitrogen. It's the typical one, usually a UHP grade um, of a bottle, and I'll default to Matt for putting any prices together on those sorts of bottles because it's independent of Gasmet. But you're only going to use about 10 liters per zero. So naturally, it's depending on the amount of times you're using it daily, etc. So that's ongoing. That's a requirement. And the second requirement from the operation is the particulate filters. So it's a two micron particulate filter. With a new unit, you get 1 plus 5 extras. We sell a pack of 10 for $70. And if you follow approximately the 3-month rule, you can see very quickly that it's it's a negligible cost. There is no need to send it back each year because that NIST, you've got a NIST traceable laser. So that in itself is your internal calibration point. And every time you're doing a zero, you've got documentation of the optical health. There's certainly keeping the gas cell clean and dry is the key component. It's not a liquids analyzer, it's purely a gas analyzer. So that's the most important. Keep that gas cell clean and dry. We do not expect to see an analyzer back under 5 years. Very recently at the Gasmet website, there was a little sort of a press done on a unit that was retired after 20 after 20 years. So economic life of these is definitely in the 10 plus range.
All right, I did had a couple more pop in here. Can you please provide a ballpark pricing on a typical setup?
Mm. So basically, how we've priced it respectively is that, as mentioned, that dual functionality. So if we're a client that just needs to quantify the known, which is going to also include that full list of 300 plus gases, the entry price is about $45,000. On that is the entry price. If we're talking to a hazmat person who we know needs the whole shebang, the whole shebang is the full software, the NIST EPA library, etc., even extra batteries. We go to a figure of just under 70,000. So for 70,000, essentially, a user is supplying their laptop and the nitrogen. We're supplying a day's training, extra batteries. 3 batteries will give you autonomous operation, cases, software, everything you need. So we've broken up for that so that people that we have some users, sometimes the hospitals have got a pretty known set of gases. They don't need to have all the power of the software. They just need the ability to go in and accurately quantify known gases. Whereas a person that is wanting to solve air quality issues is really at the higher end in the pricing.
The next question is the library list of chemicals online? I can answer that one, at least from my perspective. We have it on the RAECO Rents website under the Gasmet page in the documentation section. Jim, I don't know if you guys have it available as well online.
Yeah, it's continually updated, etc. So yes, on that, no problem. And we're generally always very interested to talk applications too, because sometimes it can be misleading. I mean, what are the gases? Because sometimes you want to know the full application. FTIR is all about knowing the matrix, the IR absorbing matrix. So it's good, and we have representatives that can talk to you about application.
Another one is, if you know the chemicals you're being exposed to, can you trust the PID direct readings? I would say if it's the only gas in the environment, you have a good chance of trusting those readings.
Yep,
your take on it, Jim?
Yep, nope. That PID or electrochemical sensor and all those, etc. I mean, they can on the same gas. If there's just the same gas, then they would produce the same readings. It's the fact is it just a single gas, or what are you dealing with? That is the The reason, but all hazmat incident response people typically have their gas detector and PID. That is a go-to, and then this is the next level to assist that next level of power to analytically solve the problem there. So they're generally used in unison for sure. A PID being your first level.
Okay. We talked about the cost of purchase. The rental costs are about not quite $1,000 a day, and just under $3,000 a week. And if you need longer, let me know. Give me a call. We'll talk about your length of rental. Next question is, how far do you need to be away from the unit if you're using the PDA Bluetooth connectivity?
The basic design was that the person, the operator, would be close by. So what we had deemed it's Bluetooth 2.0, which is 30 feet line of sight. So the idea is that you're close by. Now, there's several situations here. Is that the PDA has Wi-Fi and 3G capability, so the information can be sent very quickly remotely. So essentially, anybody if they've got 3G or the Wi-Fi anywhere in the world, but mostly incident command or that sort of thing. So that was the strategy. To keep those two relatively close, because the PDA is operating. There is no display on the 4040. It's all operated through the PDA. Taking a sample on the other side. Now, again, the line, a typical line is about 20 feet, the sample line that comes with it. However, you can have extended. We have done a test that people have asked us about 300 feet. Can it draw a 300 feet sample? And the answer is definitely yes. Delay is about 45 seconds, so you're not compromising too much to get your sample there and get your response. Alternatively, you can take a Tetla bag sample and bring it back if you want to just keep the instrument in a particular zone. Then you can do that as well on that. So yeah, there's flexibility built in as to your strategy for the sampling.
All right, a couple more. If you use a PDA on a laptop, do you need to zero check on both?
Yes, that's correct. What it is the PDA is because you need a higher end of processing here, the Fourier transformation. We take it for granted, but it is a serious amount of mathematics that was once required, was a mainframe computer. Thanks to the power of the smartphones, etc. these days. So the PDA is essentially a little computer. And so when you do the zero of the instrument, it is where the processing of the transformation, the whole algorithm is running in the palm of your hand on the PDA. We've called that software CalcMet Lite. I illustrated on my laptop the full-blown CalcMet, which is run on a laptop. So yes, so if you're going to use the PDA, you connect up the PDA to the 4040, run the nitrogen through, do the zero, and or you connect up the laptop, run it through, and record the zero on the laptop. So they both have the zero. Normally, you just choose one or the other. I'm going to run it with a PDA today, or I'm going to run it with the laptop and do the zero. And that's. But yes, the answer is you do need to zero both.
Okay, and I believe this is going to be the last one now. How do you deal with semi-volatile condensation on the mirror?
Semi-volatile condensation. Certainly, maybe more I mean, we're concerned about that if you've got the combustion, if you've got any high boiling point components. Now, assuming the 4040, if we talk specifically about this product, it's ambient air. All right. So normally semi-volatiles, if you're sampling from ambient air, unless we've got volatiles that have got the ability to condense en route, then we would have to talk through that application and be a little bit sensitive as to what the best sampling strategy could be. when you're sampling ambient air in a typical form, there's no sort of chance of condensation. But here, if you've introduced a semi-volatile, then there may be some heating required, things like that, to ensure that gas matrix now, which components could condense out, is kept above its condensation point, etc. So the point of the question is a good point, and then so all we could say is we would need to discuss clearly what components we were trying to test for, what the potential for condensation was. Gasmet has other products where we do raise the gas cell temperature, the sampling temperatures, etc., to keep the sample above any condensation. Of course, in a stack, it's all about water being above the dew point for water vapor, but it may be in this particular question and this application, it's about some high boiling point solvent or component that they're dealing with that they want to carefully or accurately sample and measure.
Okay, Jim, thank you very much for the presentation. If any of you have any more specific application questions, feel free to give us a call at 866-RENT-EHS or 866-736-8347. You can also reach me by email at matt@raecorents.com. If you want to know more about the technologies we supply, please follow us on social media. We put out lots of good technical tips on my blog at blog.raecorents.com. You can also follow us on LinkedIn and Twitter. We do record all these training sessions, which you'll find on YouTube on the RAECO Rents channel. If there are some topics you'd like us to cover in our webinars, please send me an email with the subject. We have access to lots of product and process specialists. Please let me know what we should cover by emailing me at matt@raecorents.com. At this point, if there are no further questions, our presentation will conclude. Thank you for attending.